All right, hello. Welcome to our fourth day of online lectures. Um, Today we're going to be covering binary and hexadecimal. And so we're going to start with this set of slides. There's two sets of slides that cover binary and hex. That was just because last semester they were split, but today we're just going to do them all as one topic. Okay, so let's get started. Basically, our goal today is to convert numbers from binary to decimal, and then we're going to convert numbers from decimal to binary. And then we're going to convert numbers from hex to binary, and binary to hex, and decimal to hex. There's six conversions. Yeah, the picture is from an episode where Bender has a dream. The dream is that he sees the number 2, but there is no such thing as 2, because everything is zeros and ones. All right. So what are decimal numbers, right? Basically, a decimal number is a way to write things out. There's the concept of having kind of a number without having it in any particular base, but usually you'll have a number and we'll write it in base 10. So generally, what we're going to see is something like this, where we see, for instance, 153 is equal to, really, I guess you can start at the 100 end, or you can start at whichever end you like. It's equal to 3 plus 5 times 10 plus 1 times 10 squared. So we see that the 3 is multiplied by 10 to the 0. You have to remember that 10 to the 0 is 1. So, okay, let's do it again. So 1729 is really 1 times 10 to the third plus 7 times 10 squared plus 2 times 10 to the first plus 9 times 10 to the 0. And so what we're doing here is that the digits that we use, 0 to 9, the reason why we use 0 to 9 is because 0 to 9 are the numbers between 0 inclusively, and 10 when we don't include it. So yeah, so basically we have the numbers that can be represented uniquely by some number times 10 to a power plus some number times 10 to the power minus 1, all the way down to 10 to the 0. Let me do something. There we go. Okay. So we have a number base 10. Digits are permitted to be 0 to 9. So we can all imagine where this is about to go. Here we go. So if we have some number, the number is this thing. It's 281-853-49722. So whatever the heck that is. The point is that we can write it out, and we can break it down into its digit composition. And so that's how we do it. So basically every digit has a value, and each digit has a power, right? So this power at the top is 10 to the 10th, then it's 10 to the 9th, 10 to the 8th, all the way down. Is there an easy way to convert to base 3? Not a well, so the way to convert to base 3 is the same way as to convert to binary, except you just add one more digit and divide by 3 instead of 2, but you'll see what I mean in a second. Okay, so binary numbers are kind of the same, except now we continue the analogy. Instead of, we replace the base of 10 with the base of 2. When we replace the base of 10 with the base of 2, the thing is that there's only two numbers that are possible, right? We only have 0 and 1. And so those are the only two numbers that are possible because 2 is the biggest number we're allowed to have. And so since, let's take this number at the bottom, 0, 1, 0, 0, 1, 1, 1, 0. That's some kind of binary number. And what we see is that we can convert it back to decimal by using the same power rules that, that we use for digits. When we talk about binary digits, we call them bits. So, for instance, here we have a 0 in the top place, and let's start at the other end. So we have a 0 at the bottom place. 2 to the 0 is equal to 1, but we multiply that by 0 and we get 0. 2 to the 1 is equal to 2, and in that digit, the bit is 1, so we get a 2. And so that's why the first thing we add up here is 2. And then the next thing is another 1, so 2 squared is equal to 4. And so when you multiply the bit 1 by 4, you'll add up a 4. Same thing here. 1 times 8 is going to give us the 8. And then we see that there's 2 zeros after that on our way up. So the 16's place is 0. The 32's place is 0. The last place that has a 1 in it is the 64's place, and that gets a 1. So that's basically the way to convert from binary back into decimal. So it's actually just as simple as that. What you do is you say, if the binary number has a 0 in that place, you multiply 2 to the place, or you take the power of 2 to the place. How do you get negative? We're not going to talk about that right now. So the thing is that in order to do negative numbers, there's technically two different ways to do it. There's the old way that some computers back, in the 1950s and 40s used to do it, called ones complement, where you would just have a negative bit at the top. So if the bit was 0, the number was positive. If the bit was 1, then the number was negative. But as it turns out, there is something we do nowadays called 2's complement that I'm actually not going to cover. So only positive numbers in this lecture. So and if you want to do decimals, then you have to do some kind of floating point representation. which we are also not going to cover. Those things are kind of complicated. So what is 0110 in decimal? So let me go over to my little live board, and I'm going to try to write. Unfortunately, I have lost my pen for my tablet, so I'm just writing with my mouse. So if we start with 0110, yeah, there are 10 kinds of people. So the point is here, this is going to be the 2 to the 0th place. This is the 2 to the first place. This is the 2 to the second place. And this is 2 cubed. And so when we want to convert this into decimal, what we're going to do is add up all the possible, add up the ones, essentially. So here, we have a 1 in the 2 to the 1's place, so we get a 2. Plus 2 squared is equal to 4. So we're going to get 2 plus 4 is equal to 6. Yep. Cool. All right, let's do it again. So how about 1100, 1100? So let's see if maybe I can type in something like that. So if we start with 1100, then this is in the 2 to the 0's place. This is in the 2 to the 1's place. So in the 2 to the 2's place, we have a 1. So 2 squared is 4. So, and then here we have a 2 to the 2 cubes place, so that'll give us an 8. So, yeah, this bottom little part is going to give us 12. Now this is 2 to the 4's place. Yeah, there's no conversion that I know of in Python that, or maybe there is. I think there might be. Yeah, I think there is. Let me just. I think that there are ways to do it, but I'd have to look it up. Okay, so we have 0 in the 2 to the 4's place, 0 in the 2 to the 5's place. Then we have 1 and 2 to the 6th place and 2 to the 7's place. So 2 to the 6 is 64. And 2 to the 7 is equal to 128. So when you add all of those up, I think someone already said the answer. But I'm going to pretend to compute it anyway. Yep. 204. Cool. So, all right. Well, let's look at the lecture notes and do it again, because that's what we do when we do these things. So, okay. So how do we do this one? 1010, 1100. So the trick is that we're actually not going to do this whole one. We're going to steal most of the answer from the previous answer. So if we actually wanted to do, in this case, if we want to do 1010, 1100, we can see that the answer is actually the same here. So this part here is equal to 12. And what is this part equal to? This 1010 part at the top. So this is the zeros in the 16's place. This 1 is in the 32's place, right? The 32nd place, or whatever you want to call it. And this is in the 128th place. So when we add them up, we'll get 128 plus 32 plus 12 is equal to 172. All right, excellent, excellent. So basically the point about this is that we can convert. So what are we doing now? We're converting back from binary into decimal, right? So that's all well and good. And then, of course, there's a bunch of other examples that I have written down here. You guys can play with them. They're all in the lecture notes. So there's this horrible thing. Let's just do this long one just for no reason. So it is 1, 1, and then 4 zeros. And then I think it was 1, 1, 1, 0. So normally when you write binary numbers, especially if they get long, you write them in these little 4-digit or 4-bit combinations. Technically, if you wanted to make this one complete, you would put 2 zeros at the front of it, like that. Not that it matters, because the leading zeros aren't going to do anything for you. So basically here, I'm just going to write it out. We're going to get 2, 4, and 8. And then in the 16 spot we get nothing. 32 spot we get nothing. 64, nothing. 128, nothing. This is in the 256 spot. And this is in the 512 spot. So if we want to add up all these things, 512 plus 256 is 768. And then we get plus 14, I guess. So that would be 778 and then 782. Nice. Okay. So I think it's not terribly surprising how this is going, right? So I think we can now convert from binary back into decimal. All right. So that's good. We got those plus some other ones that we didn't actually write out. So if you want to, you can always go back and do that kind of thing. Okay. So how do we convert back from decimal to binary? And I'm very sad because when I wrote this joke, or didn't write this joke, when I copy-pasted this joke into this slide, my expectation is that the vast majority of people are going to groan when they see it. Unfortunately, since I can't hear you, I'm just going to have to assume that you are groaning in spirit, or inaudibly. Very good. I'm happy to see the disapprobation or whatever. Okay. So, I think, and I kind of like the way that I think about it algorithmically. So to convert from decimal back to binary, I look at it as a bit of code. Here's the bit of code. So yeah, I do not make any claims as to having invented it, except for that misstatement that I just made, where I said I wrote the joke myself, which clearly is impossible. Yeah, as soon as our coronavirus quarantine drives us all insane, then we're gonna think that's funny. So maybe be careful. Ask yourself if that joke is hilarious, and then you'll know how far gone you are. All right, so what does this bit of code mean? Right? What does this bit of code do? So what it does is it starts the binary string off as empty. And so basically, I'm not going to convert it. So you can't really convert something into a binary number, right? Because all numbers are essentially stored as integers inside of the computer. But basically what we're going to do is while the number is not 0, so that's while number. So if number mod 2, what is that doing? So what that's doing is that's saying if the lowest digit is equal to a 1, then we're going to stick a 1 onto the front of our binary string. And I'll explain why we're sticking it onto the front. And then if nummod 2 is equal to 0, then we stick a 0 onto the front. And either way, we divide by 2. So let me just go through the algorithm a little bit and show you what it is to do this. So let's try to convert a number, 37. Let's convert this into binary. So, whoops, why did it not display? Convert this decimal into binary. There we go. So, let's follow the algorithm. So what does the algorithm say? It says first what we're going to do is the number 0? If the number is not 0, then we ask, is it even or odd? If it's odd, then we add a 1 to the end of our binary number. If it's even, then we add a 0. So in this case, we're just going to add a 1 because it's odd. And then you divide by 2. So what I mean by divide by 2 is you divide by 2 without remainder. So 37 divided by 2 in this case is just going to be called 18. Now, you might say, oh, it's 18.5. No. Always round down. The reason why is we're using integer division. Okay, cool. Then what? Then we see that 18 is even. So in this case, it's an even number, so we're going to put a 0 on the front and divide by 2. We'll get 9. So 9 is odd, so we'll put a 1 in there. And we'll divide by 2 again. Now, so 9 divided by 2 is 4. And so when you do this, you'll get another 0. I think I'm going to have to move this answer. I'm going to shift it over a little bit. And so when we divide again, we get 2, which is also even, so we get a 0. And then finally, we divide by 2 and get a 1, so we get a 1. Then we divide by 2 again, and 1 divided by 2 is 0, so we can stop. Cool. So let's just check to see. Fun fact, 2 to the 5th is not equal to 30. Very good. Oh, I see. Yeah, no, I've caused a lot of infinite regressive binary jokes. Terrible. So let's just check to make sure that this is correct. And so basically this is in the 1's place. This is in the 2 to the 0's place, so that's 1. This is in the 2 to the squared place, so that's 4. And so this is 8, 16, and finally this is in the 32nd place. What's the intuition behind it working? Good question. The intuition behind this working is basically, if I start with a decimal number and I want to convert it into decimal, I'll show you basically. So if I wanted to convert 153, which is already a decimal number, into decimal, then what I do is I mod by 10, and so I get the digit 3, and then I divide by 10, and I get 15. And then I can do the same process again. Then I just basically loop through this process. So what I do is then I mod by 10 again, I get 5, and I divide by 10 again, I get 1. So this is the mod step, and this is the divide step. And then in this case, the last thing I do is I mod by 10, I get 1. I divide by 10, I get 0. And so basically, this is showing that so the reason why you can't really do right to left with this exact process is because you would have to know, basically what you would have to do is you would have to search out the largest power of 2. And so you'd have to basically start counting your way up until, I guess I can show you an answer to that, but it works less well for hexadecimal. So basically what we've done here is we've converted 153 into 3 in the ones place, 5 in the tens place, and 1 in the 100s place. So we've converted back into 153. So the answer is that this really works for any base. You can convert from any base to another base. In this case, it works because if you look at the algorithm, the mod step in our case is when the number mod 2. So there's only really 2 options here. If the number mod 2 is true, then the number mod 2 is equal to 1. Therefore, we add a 1. If the number mod 2 is equal to 0, then we add a 0, and we still have to divide. So basically, to convert from one base to the other, you take the number, you mod it by the base, then you divide it by the base. Mod it by the base, divide it by the base. And so it doesn't matter what the base is. In this case, the base is 2. This algorithm works if you replace 2 with any base, really. You'll have to modify the if num mod 2 and else a little bit, but otherwise it's basically that. All right. So let's convert another one. Let us convert let's say, oh no, wait, we want to convert, let's convert 1729 into binary. So it works if you're going from any base to any other base. And I mean, the mathematical theory behind it is more something like any number can be written as, say, alpha I times b to the I, where I is bigger than or equal to 0. And so the thing is that you can write where alpha, all these alpha i's, are between, well, I guess this is a not equals, so let me erase that. And so given this fact, if you want to extract all the alpha i's, the one in the lowest position is the one with the power b to the 0. So it's the one without any b's on it. So if you mod by b, all of the other ones will disappear temporarily. And then when you divide by b, you shift everything down by 1 power. So basically it's basically an extract alpha 0 process and then shift everything down so that alpha 1 is in alpha 0 spot. And then you repeat. So anyway, okay, let us convert 1729 into binary. So 1729 is a fundamentally interesting number. The reason is that there's a story about a mathematician. His name is Ramanujan, and he basically the story is basically that he told people that 1729 is the smallest number which can be written as the sum of two distinct cubes. Or two distinct pairs of cubes, I should say. So as it turns out, 12 cubed is 1728, plus 1 cubed is 1729, and 1729 is also equal to 10 cubed plus 9 cubed. So that's like, you know. But you might say, what does that have to do with converting it into binary? You know, the answer is nothing. So, okay. How do we convert this into binary? So the first thing we do is we ask, is it odd or even? So 1729 is odd. So we're going to start with a 1. And I'm going to put it all the way over here so that I don't run out of space as I move this way. So 1729 divided by 2 is 864. So 864 is even, so we put a 0 in that slot. We divide by 2. We get 432. Which is also even. Put another 0. Divide by 2. That should be what? 216, right? Another 0. Divide by 2. 108. Another 0. Divide by 2. Finally, 54. Wonderful. Another 0. Divide by 2. 26. Yet another 0. Divide by 2. Finally, we get to 13. 1. Divide by 2 again, so 13 divided by 2 is 6.5, so 6. Even. Divide by 2, we get 3. 1. Divide by 2. 3 divided by 2 is 1. We get a 1. And 1 divided by 2 is 0. So at that point, we get zeros forever. All right. So, here's the question. Is this correct? Well, you might say to yourself, well, good God, this is a giant number. So let's break it down into its little nibbles, or its little quad things. So, okay. So here's what we get. We get a 1 in the ones place. Nothing in 2, 4, 8, 16, 32, 64. In the 128th place, we get a 128. But then nothing in 256. We get a 512. And we get 1024. $54 divided by 2 is 27. Yes, it is. Well, I can't divide. The good news is I think that 27 divided by 2 is still 13. Good. Okay, so only one of the bits is screwed up. So which bit is it? So it's so that one, that one, that one, that one, that one, that one. Is it this bit? Okay, well, what if I had done this one? So if I had just done this, then okay, that doesn't make sense. Yeah. Okay, so this added together only gets us to 1665. But if we add on another 64, then we get ourselves up to the correct answer, 1729. Good. So yeah, this bit was wrong because I thought I could divide 54 by 2. I think I just looked at it and thought 52 to myself because I was so used to dividing by 52 for decks of cards and stuff. Oh well. Okay, yep, so there's a little fix there. Nice. Okay, and then I added this extra 0 up in front just to complete the effect, right? We always want 4-bit combos. Just for the exactly to complete the nibble. Cool. Let's do it again. Let's say that we want to convert. Let's not do a number with 7. Let's do 8,315. And let's convert this into binary. So we start with a 1, we divide by 2. And this time I'm going to use my computer calculator so that I don't screw up. The next number we get is 4157. So that's odd. And so where is the integer thing? Huh. I don't know. Okay. So 4157 divided by 2 is 2078, which is even, so we get a 0. So then we divide by 2 again, and we get 1039, which is odd. So we get a 1. And that completes the low order nibble. So let's keep working away at this. So this is, I'll just draw a line under this so that we have some distinction. So then we get 519, which is odd. Put a 1. 259, which is odd. Oops. 259 divided by 259 is in fact 1, but that's not important. So 129. Ooh, 129. Interesting. So that's odd. So, yeah, as it turns out, at this point we can kind of cheat. Because we know that 129 is equal to the thing in the 128's place, and then a 0 in 64, 32, 16, 8, 4, 2, and then an additional 1, because it's really 128 plus 1. And so that's what we get. So we can kind of tack this whole thing onto the front. So we'll do this, and then we have this all 0 niblet. There we go. And then we have this triplet, which will complete. We'll add a 0 on the front of that, so 0, 1, 0, 0, like that. All right. Do I agree with you, D? Let's see. I think you might be missing a 1 or something. Anyway, yeah, it's hard to say. So, okay. Well, for once I'm actually right about something, right? So this is probably, well, actually the good news in life is that in previous semesters we forced people to actually do these conversions. Oops. You can't see that. That doesn't exist. We used to force people to do these conversions on exams. But it seems like that may not happen this semester. We will try to come up with some thing to test whether or not you understand how to do these conversions. But as I say, it's not free points as it turns out. The scores on these are relatively mixed, I will say. It can turn into quite the disaster sometimes. So, at least from my experience grading it last semester. But the moral of the story is, if we actually look at Python, Python has a nice way of doing this that we can check things. Well, you guys, you know, you guys can have all kinds of calculators that you want now, right? Nothing prevents you. So, note what Python does. Python will write it as 0b in front. And so the thing about that is that what this is telling you, the 0b, is it's telling you that that number is a binary number. So if we want to encode a binary number, let's say that we want to encode a binary number in Python, we write 0b, and then we say 1100. And then I'm going to print out x. Now we all know, because we've done it, 1, 2, and then 4, 8. So this number here is equal to 12. So what is it going to print? Does it print 0b1100, or does it print out 12? Well, yeah, it prints out 12. Now, why does it print out 12? It prints out 12 because once the number is stored in the integer, right? Once it's stored, your computer doesn't really know the difference between a binary number and a decimal number and a hex number, which we haven't gotten to yet. All it sees is just the bits. And so when you tell it to print out an integer, it prints out that integer in decimal form by default. And that's it. So, okay. All right. I think it's about time, if I'm not mistaken, to talk about hex. So let me seamlessly, without even let me see if I can do this seamlessly. This will be the, yes. There we go. I had to load up a different set of slides, but it's good now. So what is hexadecimal? So hexadecimal, instead of being base 2, is base 16. And so, why 16? It's mainly because 16 is 2 to the 4th, right? And so the point about that is that every 4 binary bits is 1 hexadecimal digit. And so in hexadecimal, we have 16 different numbers, each from 0 to 15. But traditionally, we don't like to represent things with 2 digits when we're doing hex. For instance, this 15 is no good, because 15 in hex is something different than 15 in decimal. So unfortunately, we cannot just write 1 5 anymore. So we need 2, not 2. We need, 6 extra symbols to play the parts of digits above 9. And so this is what we do. We use the letters A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F is equal to 15. And so if you ask, well, what is 16? 16 is equal to hexadecimal 10, right? So hexadecimal 10 is equal to decimal 16. In fact, they did use hexadecimal in The Martian. The reason why they used hex is because they were actually doing something a little bit dumber than that. They were encoding ASCII into hex and then sending the hex, which is, it's the way that a computer might do it. I'm not sure if it's really the optimal way to do it in real life. I think there's, because ASCII has so many wasted characters, there's a lot of state space that's kind of wasted if you use 2 ASCII, or you use 2 hexadecimal digits to represent every ASCII character. But anyway, so in Python, C++, and a lot of other languages, the tradition is that you use 0x and then you put your hexadecimal number afterwards. And the main reason for that is that if you put a 0x, Python will know to interpret that number as hex, because as we're about to see, 0x1234 is not the same thing as 1234. So okay, so let's actually try to compute these things. So let's see what's next. Let's actually just do some conversions. So let's try to convert. Let's convert 0, 1, 2, 3, 4 into decimal. So converting this into decimal is the same thing as doing binary, except now every place, so you have to remember that this 4 is in the ones place. The 3 is in the 16s place now, because everything is base 16. This 2 is in the 16 squareds place, and this 1 is in the 16 cubeds place. So basically, the way to look at this is that we will add up all these things. So we add up 4 times 1 plus 3 times 16 plus 2 times 16 squared, which as it turns out is 256, and plus 1 times 16 cubed. Okay. And 16 cubed, I think, is 4096. And so, okay, if we add all these up, what do we get? We get 4 plus 3 times 16 plus 2 times 256 plus nope, that's not right. That also cannot be right. The Windows calculator is not respecting order of operations. So this is 512. 3 times 16 is, I think, I'm going to say 48. So when we add all these up, that's better. So this, let's do it again. Let's convert So this is probably an example that I should have started with. This is the easier example. So we have a 3 in the ones place and an F in the 16s place. So we have to remember what F converts into. F converts into 15. So what we're going to do is we're going to write this is equal to 3 times 1 plus F, which is 15, times the 16s place. So really this is 15 times 16. And so what we're going to do here is we'll say 15 times 16 plus 3 is 243. That 3 had a tail. Okay. So anyway, there we go. Let's do a few more examples. Oh, why come back on this slide? Okay, so let's convert again. Let's say convert Okay, there we go. So if we're going to convert 3CA into decimal, then how are we going to do it? What we're going to do is remember that A is equal to 10. B is equal to 11, so C is equal to 12. And 3 is equal to 3. So this is in the ones place. This is in the 16s place. And this 3 is in the 256th place. So when we do the conversion, we'll see that we get 10 plus, well, it's 12 times 16 plus 3 times 256. And so now we just have to compute this number. So 3 times 256 is 768 plus 12 times 16. I'm seeing 790 or 970. 970. Okay, let's do one last example of this. Let's convert convert D20 into decimal. So what is D? So if C is 12, then D is 13. And so we already know the places. This is in the ones place, this is in the 16s place, and this is in the 256ths place. In fact, you can convert a hex number into binary. You can do it much easier than you can. That'll be the next thing we do. So I'll show you this last example. And so 13 times 256 plus 2 times 16 plus 0 times 1, right? Because in the ones place, we just have a 0. And so in total, what this is going to be equal to is 13 times 256 plus 32, and that's it. So 3360. All right. So cool. So I think that's enough of converting hexadecimal into decimal. So can we convert let's do the one you say. Let's convert let's see, I think this is from binary into hex, but it doesn't matter. This is converting either from binary to hex or from hex to binary. So okay, so we see that when we go from 0 up to 7, right, this is binary 0000, 0001, 0010, 0011. If you convert all of these, they're all equal to 0, 1, 2, 3, 4, 5, 6, 7. So all of these things match. So the hexadecimal matches the decimal, the binary makes sense. Okay, and then here's the place where it differs. 8 is 1000, that's still okay. 9 is 1001, and A is now 10. So that's the place where this starts to differ. And so if you want to convert from either binary to hex or from hex to binary, I'll say that you use this table. Now, do you have to use this table? No. Can you memorize this table? Yes. Can you understand this table and be able to reproduce it? Yes. There's nothing magical or mystical about this table other than the fact that it's just listing out all the answers. So, is it possible for me to make this slide smaller? Maybe put it on this side and do that. It is possible. There we go. So let's do some converting. This is nice. I actually like this because we have the table and we have the slide and we have it's very good. So converting from, let's say convert BA21 into I like that, into binary. Okay, so all you really have to do is use the chart. And so you start at this end. I don't know what the tab is. Let's see. Oh, for a 203 lecture, I was looking up different mathematical things, and this is the root structure of the group E8. All right, back to work. So let's convert this into binary. So 1 converts into binary like this, right? Actually, I might just even type it out. It's going to convert as 0001 using the table. And then what we're going to have to do, so remember to include these zeros. If you don't include the zeros, then unfortunately what it's going to do is get you the answer wrong, because you see this is in the ones place in hex, this is in the 16s place. So we need to have 4 bits in order to represent the whole thing. And so for the 2, we just copy the next thing, so 0010. And then for A, we copy out of here, so we get 1010. And then for B, we copy again, we get 1011. And so that is the conversion. So let's do it again. Let's convert 33CF into binary. And so what we're going to do is we're going to do the same thing that we did before. So we're going to say, okay, remember to start on, I guess it really doesn't matter which side you start on, so as long as you just do it consistently. So we can start from the top and just do it this way. So 3 is equal to 0011. And then we have another 3, so we copy 0011 again. And then we have a C, 1100. And then we have an F. There we go. So as it turns out, this is pretty easy. The reason why it's really easy is because the bases are multiples of, or not just multiples, the bases are actually powers of each other. So 16 is equal to 2 to the 4th power. And so that's why these things convert so directly. This is why you don't have to use the mod by the base, divide by the base, mod by the base, divide by the base, mod by the base, divide by the base thing. Now you can do that. You can still do that in this case. So you can run the same algorithm as before, but it just doesn't, it's not required because you have these tables. So let's do one more conversion. So let's convert this into binary. And so we see that in this case, we're going to have 0011 and then 0010 for the 2, 1010 for A, 0010 for 2 again, 0001 for 1, and 1111 for F. So that's really it. Okay. So now let's do the other way. So what if I want to convert will you ever use octal? I mean, in your actual real life career, probably not. Octal is funny. I mean, it has its uses maybe in assembly language contexts more, but actually you really don't see it very much. It's base 8. So basically, instead of having little... So I think probably the most useful purpose of octal is some older computer systems that instead of having 8 bits per byte, they would actually have, for instance, so octal is base 8. And so instead of having, 0 through F, you would just have 0 through 7. And so numbers can be written like, you can write a number like, 7 to 3, and that's an octal number. And so this would be 3 times 1 plus 2 times 8 plus 7 times 64. And as I was about to say, there were some old systems that used 9 bits in a word, and so they would group them into 3 octal digits. But the point is that nowadays, it's very rare that you'll see this. Okay, so now what if we want to convert backwards? So what if we want to convert from, instead of converting from hex to binary, what if we want to convert from binary to hex? Well, as it turns out, it's the same table. So what we're going to do is, if say we want to convert I've already done that. Let's convert this into hex. So as it turns out, it's exactly the same process. You use the table, except in this case, instead of going from binary to hex, you go from hex to binary. So 1101, as it turns out, is D. And one thing I'll note about hex is that there's not normally a preference between uppercase and lowercase hex. So I can write something as like 0xd, or I can write it as 0x little d. And sometimes you might feel like, oh, 0x little d is less aggressive, so I'll just write it as a little d. Okay, and then you read 0011, so that's 3. 1001, so if you pair that up, that's 9. 0101, which should be 5. And finally, another 1001, so that's another 9. There we go. Let's do it again. Let's pick some other ones that we haven't used. 1011, 1111, 0100, 0000. Cool. So the primary reason that hex exists is to kind of be a really compact form, right? So this is pretty compact. It's a compact form of binary, really. So that when you write out any hex stuff that you ever do in your future life, really what you're doing most of the time is you care about the individual bits that are going into it. So, yep. Okay, so let's write this out. 0x. 1011 is 1011 is B. 1111 is F. 0100 is 4. And then we have 2 zeros. So make sure not to omit any of those zeros. And 2. All right. Are there any questions about how to convert from binary to hex or hex to binary? I think generally the answer is understand the table. I don't know if I want to say memorize the table, because it's more important to understand how to build the table, right? Because, for instance, here, converting from A to 10 to 1010, from B to 11 to 1011, these are all direct conversions, right? If I asked you to convert from decimal 12 into binary, and you divide it by 2, you get a 0, 12, 6, 3, and 1. So you get 1100 directly. So the point is that this this table is useful in the sense that you can easily read off of it, but it's not magic, right? It's something that you should understand how to build yourself. Okay. So at this point, what can we do? We can go from binary to decimal and back. We can go from hex to decimal and back. And now we can go from binary to hex and back. Oh, I'm sorry. We have missed one. I just recall. I recalled just now we've missed one. So you know how to go from hex to decimal. But do you know how to go from decimal to hex? The answer is sort of. Sorta. But let's do some examples. The answer is you use the same algorithm as you use when you go from decimal to binary, right? And the rule is you divide by the base. Let's see if I have it. So these are some conversions in this direction. Converting from decimal to hex, right. So this is the decimal to, I mean, you can go through binary. I mean, there's no reason that you can't do this. That's totally legal, and of course this is equal to this, so there's no reason you can't do that. But basically, remember what the conversion algorithm was. The conversion algorithm was mod your number by 2 and then divide your number by 2. That's the binary to decimal algorithm. I'm sorry, that's the decimal to binary algorithm. Yes, decimal to binary. So conversion from hex to decimal is the same, or conversion from decimal to hex is the same. You mod your number by 16, and then you determine where it is. So remember that 15 is equal to F, like 10 is equal to A, and all that stuff. And then if it's under 10, you can just use the number itself, and then you divide the number by 16. And then if it's not 0, you go to step 1. So let's do some examples of this. Yep, so there we go. So let's convert directly. Let's convert. We want to convert from decimal into hex. So let's convert 2831 into hex. So the first thing we're going to do is we are going to take 2831 and we are going to mod by 16. So 2831 mod 16 is 15. So that's going to give us F. And then what we're going to do is we're going to take 2831 integer divide by 16. And so what that's going to give us is 2831 divided by 16 is going to give us 176. So that's the end of our first step, right? Our first digit is, or our first hexit or whatever, hexadecimal digit is F. We know we're going to end up with about 3 of them. And so what we're going to do here is then we can mod 176 mod 16. As it turns out, I think 176 mod 16 is 0. Yes, it is. Always want to double check when I'm doing a lecture, because otherwise I will say something wrong. And then 176 divided by 16 is actually just equal to, straight up, it's equal to 11. So as it turns out, and now that's the end of step 2. So we get a 0 here. And then we will, let's see, okay, that's fine. Let's make that 0 a little bit bigger. And so then finally, 11 mod 16 is just equal to 11. And 11 integer divided by 16 is 0. So this is when we stop. So the question is, what is 11? 11 is, well, so 10 is A, 11 is B. So this is B0F. So that's the hexadecimal equivalent of this. All right, let's do it again. Let us convert. I don't know. 327 into hex. So if we convert 327 into hex, the first thing we do is take 327 and we mod it by 16. Which is 7. And then we divide. So 327 divided by 16 is what? Is 20. So that's the end of the first step. Okay, cool. So now, it's pretty easy to see that 20 mod 16 is going to be equal to 4. And 20 divided by 16 is going to be equal to 1. And so finally, 1 mod 16 is 1. And 1 divided by 16, whoa, is 0. So knowing all of that, we can, so this tells us to stop. And so now we can combine everything into one hexadecimal number. So as it turns out, this is 0x, and then we have to remember that we're starting at the low end. So if we start at the low end, we'll get a 7, and then we'll get a 4, and then we'll get a 1. Or you can read them backwards and get 147. And so this is the hexadecimal conversion. Let's do one last one. Let's convert 31,825 into hex. So this is a decimal number. Let's convert it into hex. So 31,825 mod 16 is actually equal to 1. Who knew that? And 31,825 divided by 16 is equal to 1989. And so the reason is that we can do like larger numbers like this with regard to hex is because you'll see how fast these things diminish. So for instance, 1989 mod 16 is equal to 5, and 1989 divided by 16 is equal to 124. Nice. And so you see that because 255 is FF, we're going to get down to 0 by the next 2 hexadecimal digits. So 124 mod 16 should be what? -4, so that'll be 12. Yep. So 124 mod 16 is 12. And 124 divided by 16 will be 15. Oh, I'm sorry. No, it won't be. It'll be 7. So 124 divided by 16 is 7. And then finally, we will have 7 mod 16 is 7. And 7 divided by 16 is 0. So at this point, we can just read off the answer. So it'll be 0x, 7, but now we have to know what 12 is. So what is 12? 12 is C, 5, 1. Cool. All right. So that is that for hex, binary, and decimal conversions. I think that should be all for today. Granted, I've gone 3 minutes over. I was just using the Windows calculator because I'm lazy. Yeah, so in terms of our exams, we are pushing the exam back 1 week. So I am going to do that, yes. So basically the exam will be issued Wednesday, not next week, but the week after. And the reason is because it's, I certainly don't, so I can do some mental math in my head, but I can't do it reliably when I'm lecturing, because if I'm talking and thinking and writing and clicking at the same time, my multitasking abilities for calculation seem to be kind of erroneous, so it's better if I don't. Anyway, yeah, so the exam will be, what's the Wednesday after next Wednesday? So next Wednesday is the 8th. The exam will be the 15th. But it's going to be kind of a project type of thing, so you'll have a few days to do it. I think that will give you probably 2 or 3 days to do the exam problems. They're going to be like homework questions, but they're going to be more like what we put on the exam. So it's going to be kind of an average. So in terms of the difficulty, it'll be less than a homework problem, but more than what you saw on the previous exams, because on the previous exams, you had to write it, and now you'll have... No, it won't be really difficult. It's going to be the midpoint in terms of difficulty. All right. Is that it for questions? I think it's time to sign off. Thanks, everyone, for coming. I'm happy to see that everyone's still alive and converting numbers into other numbers. Or I guess I should say converting numbers into the same numbers in different bases. In terms of the project, I would say that you should limit yourself at about 200 lines. And I say that as the upper limit. If you're exceeding 200 lines, you're doing too much. If you're under 100 lines, I think you're very optimal. My code was not under 100 lines. So somewhere in that range is a decent... 260 isn't terrible. Maybe I should say that the limit is 300. I don't know. So don't take any limit I say too seriously. Just do not produce 1,000 lines of code. So I take the 200 limit back. Do not produce 1,000 lines of code. You should preferably not produce 500 lines of code. I think the thing about the project is that the hardest thing is the load map function. The actual playing of the game is... Yes, I mean, if it works, then you get the points. I'm just saying, save yourself the effort. You won't get points off if it's 1,000 lines, but if it's 1,000 lines, we will scan those 1,000 lines and find out which ones are not necessary, if you know what I mean. So so that's the answer to that kind of question, is that if it's 1,000 lines, my guess is that 800 of those lines are probably extraneous. Okay. Well, again, thank you everybody for coming. It's nice to talk to myself for an hour every day. So, all right. I'll sign off. If you have any other questions, you can ask them by email or... Oh, so my tip for the map file is make sure that you stick... My hint is dictionaries, and inside the dictionary should either be a list or another dictionary. That's also true. White space matters, yes. No, I certainly don't want 200 people talking back to me. I prefer the text. It's much easier to read what you guys have to say and to respond to it than to listen to all the people shouting at me. But that's a different story. All right. See you guys later. Have fun. Have a good day. Outro time.